Welcome to episode 51 of Fresh Thinking by Snowden Optiro. My name is Gregory Zhang. I am a Geology Consultant with Snowden Optiro. Today I will talk about the MIK Localisation, illustrating its practical application for addressing complex data challenges with a focus on the gold deposit. So a little bit of introduction about myself. I'm a geologist with over 10 years experiences in resource estimation, exploration, and academic research in multiple commodities. So I've worked over 70 projects, including resource estimation, audit, review, or due diligence for gold, copper, nickel, iron ore, cobalt, mineral sands, and PGE across most continents. My areas of expertise include resource review, resource estimation with linear and nonlinear estimation methodologies, bilingual working languages in English and Mandarin, and project management. So I have a strong capability in workflow automation while scripting and extensive experiences in mining software, including Data Studio RM, Supervisor, SERPAC, and Leapfrog. So I present Snowden Optiro's professional development courses in both English and Mandarin. Okay, so today we'll talk about the MIK. So what is MIK? MIK is short for multiple indicator kriging, and it has been used in the minerals industries for some decades. As one of the nonlinear estimation methodologies, MIK has advantages related to resolving multiple or mixed population, high variability data, and a strongly skewed distribution. What are the nonlinear estimation methodology and want to use? So nonlinear means that the resource variables, such as ore grade or mineral content, does not have a normal or Gaussian distribution, but instead has a skewed bimodal or complex distribution that can't be adequately described by a mean and a variance. So nonlinear also means that the resource variables do not have a linear or proportional relationship with the spatial coordinates, but instead has a non-stationary or an isotropic spatial structure that varies with location and direction. So nonlinear estimation methods are designed to account for these nonlinear features of the resource variable and provide more realistic and unbiased estimates of its distribution and uncertainty. So these methods can produce more accurate and unbiased estimates of recoverable resources and their uncertainty than linear estimation methods such as ordinary kriging. And nonlinear methodologies are often considered during the early stage of mineral projects when data is relatively sparse and some notion of mineable resource is required for a given future grade control configuration. So what are the high-level workflow of MIK? So MIK provides a point estimate of the conditional cumulative distribution function as at unsampled locations, while the estimation of probabilities at various thresholds. So 10 to 15 thresholds are usually selected based on the sample cumulative distribution for each mineralized domain or ore zone. For each threshold, the samples above the threshold are coded as 1 and samples below as 0. Often the inverse coding is applied, resulting in complementary probabilities. But essentially, the samples are treated as binary indicators. Variogram models are built leading to an estimate at a relatively large block scale, or it's called panel scale. So the estimate result at each location is a consequence of the probabilities between 0 and 1, so forming a CCDF. The total of the probabilities at various thresholds will equal to 1. There are invariably order correlation issues whereby the successive probabilities are not monotonically increasing, and the 3 solutions can be used to address these issues. And then how to conduct MIK. So it follows a similar workflow as linear estimation methodologies. So first step is always a statistical analysis. And then we would select indicator thresholds and transform the grade into a binary data for every threshold. And then modeling of the indicator variograms. After that, we'll model lower and upper tail of the distribution. And then ordinary kriging of each indicator threshold. Essentially, we're estimating the probabilities. And then post-processing to produce the E-type estimates. And then most importantly, to do the model validation. Are there any tips about using MIK? So always make sure there's only gradual change between the threshold variogram models. So each threshold variogram models uses all the data. So only difference is the cutoff value. So for the high cutoffs, most data will be coded as 0, which is lack of the variability. And therefore, often we have to improvise some variogram models based on the lower cutoffs. We often use the same search neighborhood for all the thresholds to minimize all the correlation issue. In the first part of this estimation, we need to make it really robust, get the robust estimation result. It's very critical. And after that, because all the following work relies on it, therefore the validation is very important. So next question, what is the change of support? Why is that necessary? So since the initial MIK distribution as estimated is always strictly at point support, so a change of support correction needs to be applied to each CCDF to reflect the distribution at the panel scale. A number of options are available for this change of support, given that in the case study and in most cases, the CCDF are positively skewed. And this is always the case for the gold deposit. And indirect log normal correction is an appropriate change of support algorithms. This can be carried out using the open source GeoSleep software. This can be carried out using the open source GeoSleep software, and that includes two stages. So the first corrects the point CCDF to the panel CCDF using variance reduction based upon the relative point and the panel block sizes. And the second process forces the panel support average to match the point CCDF average. Because we've already finished the MIK point estimate at a centroids of a larger block size or panel size, and then we need to do the change of support from the point estimate into the panel block scale estimate. After that, we will need to do the localization and put the results, change it into the SMU scale. So why do we need to do the localization part? It's because the need for recoverable resource estimates raises the importance of post-processing or localization of the MIK estimates to the future mining scale. However, only a few case studies in the published literature discuss such post-processing details. Therefore, there's value in sharing our thoughts and experiences on this topic. So let's talk about some details of localization. So the first step is to do the change of support. And we need to calculate the within block variance. And by doing that, we can use GeoSleep software, which is called gamma bar. And after that, we'll calculate the variance reduction factor. So essentially, that's the ratio of the variance at the smaller scale divided by the larger scale. And then we use the indirect log normal change of support and change that from the point to the scale, panel scale. After that, we will run the ranking estimate and flag the SMUs in each of the panel from high to low. And so we can assign the localized values into the different SMUs. And after that, most importantly, is to validate the results. We can't overstate the importance because this is a very complicated procedure. and it can go wrong at so many places. So we always validate our results. So let's talk about some validation tools we could use especially for MIK. So the first is to compare the CDF before and after the change of support. So first is to compare the CDF before and after the change of support, because we would expect more variability at the smaller scale or at the point CDF. So after the change of support, the CDF at the panel scale would be expected to have less variability, and therefore the CDF will be relatively squeezed towards the middle when you compare to the point CDF. And after that, the second point is to we can compare the average of the SMUs. And the second, we can compare the average grade of all the SMUs inside one panel and compare with the E-type average. So by doing that, we should expect these two values be very close. In other words, there should not be any extra metal created during the change of support process. And then we can compare the global statistics. We can compare the average, the skewness, and do some QQ plot between the composites and the SMU grades. Let's talk about one case study where we use a localized MIK. So most of the time we use localized MIK during the relatively early stage of the projects. One, it has not come to the grade control stage. So one of the projects we applied is a gold mine during the exploration stage. We were requested to run the LMIK for the mine planning and also compare with other nonlinear method, which is called localized uniform conditioning, or LUC. So we did both estimates and run the pit optimization separately and compared the RPEE constrained resources. It turned out the LMIK gives higher tons, grade, and metal after certain cutoffs, and the differences are enlarged as the cutoff grade increases. So what's the reason for the difference in the LUC and LMIK results? Because LUC makes certain assumptions regarding input data, and the UC requires the multi-Gaussian relations between the transformed data, including sample, panel, and SMU supports, which can't always be met and can never be verified. So the high CV feature of the highly skilled data in this case leads to more potential for high-grade smearing, so which is challenging for LUC. So the high CV data has to be remediated before estimation at the panel scale, OK estimate, for the application of UC. A high yield spatial constraint has been applied in this case instead of a more conventional top cut. So the metal and average grade therefore decreased by 7% when compared to the MIK parent block. LMIK doesn't require top cut, while the modeling of the upper tail of the CDF. So that portion of the distribution above the uppermost indicator threshold. So since we've already mentioned the LUC, here's a high-level summary of the method. So the first is to estimate into the panel with linear estimation methodology, for example, by ordinary kriging to ensure the minimum conditional bias, and then test that various support maintains a multi-Gaussian relationship, which is theoretical test, and then create a discrete Gaussian model at point support, panel support, and the SMU support. Then transform the cutoffs into the Gaussian space via anamorphosis and derive the model and proportion above each cutoff. Then translate the corresponding metal values and cutoffs from Gaussian space to the regional space. And the last, generate the ranking estimate and localize to SMUs on a metal basis with the grade being back calculated. So since we have the estimated grades into the SMU already, do we still need to do any grade control drillings? So none of these non-linear estimation methods can save the step of grade control drilling. It's only a way of evaluating the potential recoverable resources before drilling the close distance holes. So this will give us a starting point to consider where to put the close space drilling and de-risk the project. For the mining engineers, they can use this and do some strategic planning work and treat this as the upside scenario for the evaluation. That draws this episode to a close. Thank you for joining us on this podcast. If you would like to listen to more of our fresh thinking by Snowden Optiro, you can find them for free on our website, Spotify, YouTube, Apple Podcasts, Google Podcasts, and most other podcast platforms. Thank you.